You have an array of numbers and a limited number of magic flips. Each flip turns a number positive or negative. Your goal? Wield these flips wisely to make the total sum as large as possible. Sounds simple, but picking the wrong target can cost you the entire game. Here is the challenge. You receive an integer array and an integer k. You must perform exactly k negation operations. In each step, choose any index and flip its sign. After all k operations, return the maximum possible sum of the array. The core difficulty lies in prioritizing which numbers to flip when k is smaller than the count of negative numbers, or when you have leftover moves after eliminating all negatives. The naive approach is to repeat a linear scan k times. In every iteration, you find the current minimum element, flip it, and move to the next step. While this works, it is inefficient. You are rescanning the entire array k times to find the smallest value, leading to a time complexity of O, k times n. If k is large, this redundancy is unacceptable for production code. The key insight is that sorting the array gives us immediate access to the most impactful candidates. First, sort the array in ascending order. Iterate through and flip every negative number to positive, decrementing k each time, as long as k is greater than 0 and we are still on negative values. This greedily maximizes the sum. Once negatives are exhausted, if k is still positive, we must flip the smallest absolute value remaining. If the remaining k is even, flipping the same number twice cancels out, leaving the sum unchanged. If k is odd, we lose exactly twice the value of the smallest element in the modified array. So, we simply subtract twice the minimum absolute value from our total sum if k is odd. Let's trace the example with the array 4, 2, 3 and k equals 1. After sorting, we have 2, 3, 4. We scan for negatives. The first element is positive, so the loop to flip negatives doesn't trigger. We are left with k equals 1 and an all-positive array. We calculate the sum, which is 9. Since k is odd, we must perform one effective flip. We identify the smallest absolute value in the current array, which is 2. We subtract twice this value from our sum. 9 minus 4 equals 5. This matches the expected maximum sum. The final result is 5. This is correct because we were forced to flip the smallest available number, minimizing the loss to the total sum. You'll spot this pattern when you see a fixed number of operations that can flip signs or values, and the goal is to optimize a cumulative sum. The signals are a mix of negative and positive numbers, where the order of operations matters based on magnitude. The time complexity is dominated by sorting, making it big O of n log n, logarithmic time. The space complexity is big O of 1, constant time if we ignore the sorting overhead, as we modify the array in place. Try the next problem with a similar greedy flipping pattern. Subscribe for more high-impact algorithm breakdowns.